Hello everyone. In this video, I want to show you how to create a map from the 2D environment here. And again, you can make it 3D, but here for simplicity, we're gonna consider this 2D version of it, like a view from the top. So we have our robot, the Pioneer P3DX, going through the room, and it is gonna use a left wall following, and it is going to read the front ultrasonic sensor data and creates a simple 2D map. Now, the way it does it by exporting the data to a text file, and then I will show you another code in MATLAB that will read the text file and generate a 2D map of the environment. So again, this problem is 3D, right? So you can see it's this one, but here it's better to consider it and looking at it in 2D because we want to do that for better understanding. So here is the script, which I'm going to share as well with you. The logic of the left wall follower is exactly like my previous video on this playlist that I showed you how it is working with the PID control and anti-wind up and obstacle detection. Now, the only thing you add is basically detection of distance from the front sensors and saving it into a text file here. So if we go down, most of these parameters are exactly again like the last video, no difference. Getting the sensor handles, the robot handle, the motor handles, all of these parameters that you want to set. Everything you need some previous error, previous derivative, previous time and integral for the PID controller, setting them to 0, and the time you get it through get simulation time, and then every basically 5 seconds you are going to save it here, and that can be seen down here in line 169. If t minus last save time is bigger than save interval, then go ahead and save it. So this is exactly what it is doing, and the way you save it is using this function called save map to file. So here, let's look at this main function. That is the only difference, as I said. So if you look at it, here is first it says if the number of map points is equal to 0, then return end. Okay, so here we need to look at this map points. What is the map point here? And you see that initially the map point is set to 0, but as we go on in the code, you see here that you get this function that generates the map point. This function is called sample front points. So it basically samples from the front sensor points, okay? And the way it does it is it says if not road header, then table insert. So what it does, it is in the map points, it is going to insert basically the robot initial X, initial Y, initial Z. So this is like the headline of the text file, okay? And then road header becomes true. So this function is basically making sure that it gets the initial position and starts the header of the text file. Let me show you the text file here. So if you look at the text file, look, that's this line here. It says robot pose 1.45, negative 125, and 0.13. And that is exactly basically this location here, right? The location of that coordinate system in X, Y, and Z, X to the left, Y downward, and Z out of the board or the window in this case. That is basically creating the header line, okay? So going back to the code. So that is the first part of it. That is basically the header line. Now, as you move on, this one here, this function sample front point, we saw that it does the first line, but now you can see that as we go down here, it is gonna insert more data into it. What is it that it does? If you look here, you can see that it inserts the WX and WY into the file, and W here stands for the word coordinate. So this X and Y that we store in this text file should be with respect to the word coordinate, and that is the most important thing you have to pay attention to. You cannot get the distances that you get directly from the sensors and store them. You have to transfer them back into the word coordinate because they are taken at different robot location and different robot orientation. And if you don't put them back into the word coordinate, you cannot simply accumulate them. So here is the transformation done to take your robot back into your sensor data back into the word frame here, right? So look, the way you do it is first you get the sensor word position, you say sim get object, and you look at that sensor, you get X, Y, and Z of that sensor location. Another thing you have to pay attention to is not all sensors have the same position and the same orientation as the body of the robot. Each sensor has a different position and orientation. So again, if you look at this picture, while the robot coordinate frame could be here on the top at the center, you see that each one of these centers has its own orientation and a location with respect to the center. Although they are fixed with respect to the robot, but clearly these different locations and orientations would cause distortions in the numbers. So they should all be fixed. Otherwise, your data are not going to be super meaningful. So you see that not only I will get the position of that sensor, I also will get the matrix. And matrix, remember, is a 4x4 matrix, which has the 3x3 first part of it is the orientation or the rotation matrix, and the last column is basically the position, right? Or basically these numbers here. So look, you're gonna get it, and then you say Fx, Fy, Fz is M1, M2, and M3. And these would give you the unit vector for the angle theta for each sensor. And so if you use the X and Y of it, which are cosine theta and sine or negative sine theta, depending on how it's written, then you multiply it by the distance and adding it to the sensor location in the word, that will give you the coordinate of the sense point in the word frame. And now you can add it to the point map, okay? So that's why, if you remember, if we go down and look at this text file again, you see that as we go down row by row, it's going to give you the X and the Y of the sense point. That is a point on the walls in the word frame here. Okay, so going back here, and you can see there is a \n, of course, so you go to the next line. So here we generated all of this data, and now we're going to open up a file. And we're going to open it for writing. So you see I'm using IO open. So I'm going to open up a file, and the map file name here is provided. You see it's on my local folder. The name is XY points that underscore points that text. So I am going to open that file here for writing, and then if the file could not be opened successfully, it's going to return. Otherwise, it is going to write the map points as a table, concatenate it, write it, and then, as I said, you have to close the file. Anytime you open a file, you close it. This is the PID control, and this is the periodic save. So once you make those points periodically, you are going to save it. You're not going to keep writing the data at every simulation step, because let's say simulation step is 0.005 or something, right? So here we can go and look at that. Let's see. In this case, let's actually go here and look at the simulation setting. So you see that for dynamic or simulation is, even if it's 0.05, so in every second it is going to write it 20 times. And that is going to make your code extremely slow, but I set it to 5 seconds. So only 100 simulation steps, one of them will be saving the data to the text file. So it's speeded up. So as you saw, this is my text file. And again, here, look, this is the robot running and doing the wall following, continuously reading the data from these front sensors and basically writing them to the file. Once the even one round of the robot is complete, it goes one round around the room and comes back to the start point. The text file should be good for plotting into MATLAB here. So here you see the robot is going, and this is my MATLAB file here, which is going to read the text file, and it is going to generate a 2D scatter plot for the text file. There we go, something like this, okay? So now if you look at here, that's basically what you're doing. You're getting the file name and trying to open it, but first check, make sure the file does exist. If not, throw an error, okay? But if it is, go ahead and open it for reading, and then start the robot pose and the XY points as empty. Then while you have not reached to the end of the file, keep reading, okay? With first get rid of the spaces, and again, if that line is empty, forget it, move on to the next line. Other than that, you're going to use scanf here to read the file, to read the data. And if the number of parts is 3, which means if you stored the points x, y, z, but here we only stored x, y, so we're going to only this part will run. And so it is going to read the x and the y and store them into the xy and close the file. Again, if the data that you read is empty, go ahead and throw an error, which means there is nothing saved to the file. Other than that, here you are trying to remove the duplicate parts by using the command unique. So try to, if there are 2 points that are exactly the same, get rid of them. So that is a basic filtering that you are doing. You can remove the points that are outliers here. And finally here, you are going to plot it, okay? And here is the plot. Let me plot it for you. See there RO, which means and then the marker face color is red. If not empty. So this is the robot pose. It is red, a red circle filled red. That is the initial position. That is the reading of the first line. And then the rest of it is what? The rest of it with all of those black points are the points that are taken from the sensor. And of course, it's not perfect or anything, but you can see that it has the map of the room. This is the wall extruding out and then going back to the start point. So if you put this right next to this one, you can see that actually they do match, right? So let me just put it side by side so you can see better, right? And you can see that it is actually generating the map of the environment. So I'm going to share with you the script in Coppelia. I'm going to share with you the MATLAB file, and hopefully you should be able to do that for a basic map generation, at least a 2D map generation here from the environment. If you want to do 3D, then you have to put a Kinect on the robot and get the data from the Kinect, know the values for the camera, or at least the depth map, the values for the depth map of the Kinect, and you can generate a 3D map of the environment. And let me tell you about that as well here. So if you want to bring a sensor, right, a Kinect, so you go here, then you find the Kinect and you're going to add it to your robot, right? So you're going to bring it like this. Then you can pick that and the robot and go here and then apply the same position to both of them, and then you can apply the same orientation to both of them, and then you can pick this Kinect and bring it up a little bit. So Look here. So I'm gonna lift it up a little bit. Seems like the orientation is not correct. So I'm gonna rotate this guy, putting it at 90-degree angle like this. Now, here, this Connect is gonna look at a lot of things on the robot itself. Okay, you see here, it is gonna show a portion of the robot, and here, of course, since you didn't make it a child of the robot, it is gonna be left behind. So one thing you wanna do first is make sure that the Connect does actually belong to the robot, so it moves with it. And as I showed you, you need to bring the Connect forward so it doesn't see anything from the body of the robot, only sees everything from the basically the scene, something like this. Bring it this close. So now look, when you run it, you should only, if you look at the depth, you should only see the depth from the environment. Okay, yeah. And now if you want to know the properties of the depth camera, you go here to the Connect, and if you open it, you see that a Connect has two vision sensors, RGB and depth. Okay, you see them? And the depth has its own basically script, which basically doesn't do much. But if you want to know about the properties of this camera, double click here. And now if you go there, you see there are some things, but not much. But this is the part that you care about. There is resolution of the depth map. There is the field of view, right? 57 degrees. And then there is the near and far clipping plane. So these 5 information are extremely critical if you want to use Connect to create a 3D map of the environment. So I'm not going to do it here, but just wanted to explain it to you that this is how you can make a 3D point cloud using the Connect. So hopefully the video was useful to you, and I'll see you in the next lecture. Thank you.